Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to go through a specific section in Chapter 3, how to deal with hyperbolic functions. Now, when talking to some students, I found that in some Calc 1 classes, you may have talked about hyperbolic functions, but we want to review it again because we are going to use these functions more and more moving forward, and we also want to be able to establish the integrals for them as well. To start off with, what I want to talk about is what sine and cosine would mean in the complex plane, because this is kind of diving into a field known as complex analysis. The complex plane is something that you have talked about, albeit briefly, in Math 1060, where you're dealing with a plane that is the real plane or the real axis, and then you also have the imaginary axis. So you have the real versus the imaginary. And when you're dealing with this complex plane, a lot of the functions that you're used to in the real plane, the Cartesian plane that we are typically working with, don't really apply, and there are other representations of that. And what we have here are how to represent sine and cosine in the complex plane. So we have both of these two formulas. Now these two formulas are not ones that you're going to need to memorize, but I use them because they help us identify the ones that we are going to use. The first thing that we are going to need to be familiar with is what is called Euler's formula. And Euler's formula is what happens when you combine these two in a specific way, using a function that we've also talked about back in Math 1060 called CIS, otherwise known as cosine I sine. If you do cosine plus I sine, you can get the result of what is Euler's formula by simply simplifying the complex representations that I have above in here. So we have cosine represented as this part, so e to the it plus e to the negative it over 2. And we have I times sine represented as this. Now, since we have I times sine, what that really leads us to is to eliminate that I and that I on both the top and the bottom, so both of them cancel out. And all we have left is all the exponential functions adding and subtracting together, divided by a number 2. Well, I see that this plus e to the negative it and this minus e to the negative it cancel out. And so on top, I'm left with 2e to the it all over 2, which will cancel out and give us overall e to the it. Therefore, we get Euler's formula, known as cosine plus I sine, or CIS of x, equal to, well, that really should be, these should all be x's here, really equals e to the ix. So these variables should really equal each other. Either make them all t's or make them all x's, whatever you want to. But that's Euler's formula, sometimes known as the most remarkable formula. It's showing a relation between the real plane using trigonometric functions and the complex plane using e to the it. It's really hard to connect those directly to each other. Now, with this, what we can also do with the representations from the complex plane, what we can also do is establish the two formulas for the hyperbolic trig functions that we are going to use a lot in this section. So these two are the ones that we are going to use pretty often to solve almost every single problem. These are trig functions that help define coordinates for a hyperbola rather than a circle. Now, if you remember back in 1060, sine and cosine are supposed to represent the well, the y and x coordinates respectively for a circle. So if you have a circle on an xy plane, then this coordinate here is defined by cosine of whatever the x value is and sine of whatever the x value is. So that's how we would define that point there. And the same thing for any other point on the circle. But if we're dealing with a hyperbola instead, then we can also define the points using what are going to be called the hyperbolic trig functions. To isolate the hyperbolic trig functions, what we're going to do is take our previous equations for sine and cosine in the complex plane, and what we're going to do is replace t with ix. Doing so means that every time that I had t, I would replace it with ix. So in each of these exponentials, they will become I times ix and negative I times ix. I times I will give you negative 1, and negative I times I will give you positive 1. And if we put those back in a more sensible order, using the positive exponent first, then we get e to the x plus e to the negative x over 2 equals the hyperbolic trig function for cosine, which is called cosh, or C-O-S-H. So this is cosh of x, or cosh. You can also do the same thing with I sine, putting in ix into where t is, but what we're also going to do is introduce a negative I out front. Negative I sine of ix is actually what the hyperbolic trig function for sine is, so it's a little bit different. And solving through the same way that we did before, crossing out i's to get a negative 1 there, and then that negative 1 will distribute out to switch the places of these. We get e to the x minus e to the negative x over 2 equals sinh of x, or sine hx. Again, that h is saying hyperbolic. Now, these two functions I already have boxed in red, and the reason is because these are going to be the most important ones. These will be the ones that we use to solve for specific values of functions, and also solve for a lot of proofs that we'll see in this section. So make sure these two are the ones that you really get down. Okay. Now, what these look like on the Cartesian plane. If we were to try to graph these, what we would try to consider is what these values mean. Because if I see this for cosh, really, if I see e to the x plus e to the negative x over 2, what that really makes me think about is if I were to take two values like a plus b and divide by 2. This looks like an average. This looks like an average value. We even just did average value in 6.5. So if I want to think about graphically what this would look like, I would take both ex and e to the negative x and find the average of the two. Or really, just put them all together. That's what's going to happen. So what we're going to do graphically to identify what cosh looks like is to take both these functions, and really the two functions we're going to take is if we were to do e to the x plus e to the negative x over 2, and we split that to get e to the x over 2 plus e to the negative x over 2. So we're getting two functions here. What we're going to do is add both of these together. Now, e to the x over 2, e to the x looks like an exponential function that goes through 1, so e to the x looks like this. But if I were to cut in half, what I would get is that it goes through 0.5, so around there. So it goes through 0.5 and it still continues exponentially, just not as fast. Same thing with e to the negative x over 2 would still go through 0.5 instead of 1, but it goes up into the negative x direction. Draw that a little bit better. Something like that. Okay, there we go. Now, if we add both of these together, what we get is these two values added together, 0.5 and 0.5 for both functions, add up to a total of 1. And then as I keep adding them together, what I get is a function that gets closer and closer to each of these. Because when I would add, say, this value together, I'd add this value with this value here. So both of these added together would give you up to this point. And as this function gets a lot smaller, then I'm just adding just a little bit more to my new function to get what cosh is going to look like. So cosh is going to look like a function that starts at 1 and approaches both e to the x over 2 and e to the negative x over 2. So the blue function here is cosh of x, where this black one is e to the x and the other black one is e to the negative x. Well, each of these over 2. That's what cosh looks like. Now, sinh is going to look kind of similar. What we need to do is graph the two functions that we have inside of sinh. So in this case, we're going to take e to the x over 2, and we already graphed that one, so we know what that one looks like. And we have to subtract away e to the negative x over 2, or add a negative version of it, which is more what we're going to consider. So the first one, e to the x over 2, we can draw that. We draw that before. It goes through 0.5. It goes up like so. That'd be e to the x divided by 2. Now, e to the negative x over 2 would follow just like e to the negative x over 2, which looks like this. That's what e to the negative x over 2 looks like, but we're going to flip that over the x-axis. So it's going to look like this. Going through negative 0.5, it's going to go through this. That's what e to the negative x all over 2 looks like. And like with cosh, the graph of this is going to approach both of these. It'll meet in the middle here 0, because when I add positive 0.5 and negative 0.5, it equals out to 0. So I'll get a function that curves up through 0 and curves up this way. So it looks kind of like a cubic function, where a cubic function looks kind of like this, where it goes through 0 and tapers off for a bit. It's similar to that here as well. So maybe if I graph that a little bit closer. Yeah. So it looks a little bit like a cubic function. Now, note that because the cinch both passes the vertical line test and the horizontal line test everywhere, that means it is what we call a one-to-one function, which means that for each x value, you get a unique y. You're not going to get that repeated y value for any other x. Cosh, unfortunately, is not one-to-one because it does fail the horizontal line test. I can come up with some x value that will have a y value that I can get using a different x value. So, say I could use 1.4, I could also probably use negative 1.4 and get the same y value. So that means it is not one-to-one. This is going to be something that we're going to touch upon later, but just keep in mind that cinch is one-to-one. Cinch is a one-to-one function, but cosh is not. Okay. Now, we've defined both cinch and cosh, and we have those formulas that we are going to use. And we can also define the other hyperbolic functions, but we're simply going to do so in terms of cinch and cosh. There's no need really to define anything else or use any other complicated terms. We're just going to use the same terms that we would use really to come up with tangent, cotangent, secant, and cosecant, but we're just going to put them in terms of the hyperbolic versions. So the hyperbolic versions, we have tanch, we have koch, we have seish, and we have kish. Kish is kind of the weird one. The other ones you could probably get just by looking at the word and trying to make it into a pronounceable one. But kish is the only one that's weird to pronounce. So these should look like what you're used to. Tangent is supposed to be sine over cosine, so likewise tanch is sinh over cosh. Cotangent is cosine over sine, so likewise cosh is cosh over sinh, and on and on. Now, with these definitions that we have, we should be able to find numerical values of some of these functions. For example, sinh of 0. Well, I know that sinh is defined as e to the x, which in this case is 0, minus e to the negative x, which in this case is still 0, divided by 2. Well, e to the 0 is known as 1, e to the 0 is still known as 1, so it's 1 minus 1 over 2, otherwise known as 0. So sinh of 0 is 0, which we already know because we graphed that earlier. Sinh of 0 is 0. But we can also find some other more complicated ones, like tanch. Tanch of 1. Well, tanch of 1 is going to be sinh of 1 over cosh of 1, which you can use the graphs to identify what each of these are going to be, or we can use their functions. Note that sinh would be e to the x minus e to the negative x over 2, and cosh would be e to the x plus e to the negative x over 2, so that means the over 2 parts should eliminate each other. Therefore, we don't even need to consider it. We can just say sinh is e to the 1 minus e to the negative 1 over cosh, which is e to the 1 plus e to the negative 1. So we basically have it here. We more or less have the function as e minus 1 over e and e plus 1 over e. We could solve for each of these, but we can note that this is going to be something that's going to be a little bit less than 1. Without even using a calculator, I should know that, because e minus 1 over e is going to be less than e, and e plus 1 over e is going to be more than e. So this is going to be something like e minus, let's see, 1 over 2.3-ish or 2.4-ish would be like, I don't know, minus 0.38 or something like that. And then e plus 0.38. So it's not going to be that much of a difference, but it is going to be slightly less than 1. But that would be the numerical value of it. And if you do put this into your calculator so we can find this, so we can get an idea, if we do e minus 1 over e, and we divide that by e plus 1 over e, we get 0.76. Yeah, so something less than 1. So that would be tangent of 1. Now, cosh of 5 would work the same way. Cosh of 5, well, I just use the definition for cosh, which is e to the 5 in this case, plus e to the negative 5, all over 2. Note that the only difference with sinh and cosh is that symbol in between the two exponentials. With cosh it's plus, with sinh it's a minus. So we can solve for these, although this is going to be a rather large number, because e to the 5 is going to be very large, e to the negative 5 is going to be very small. So this is going to even get pretty close. It's going to be more or less the same as e to the 5 over 2. It's not going to be too much different from that. And we can even prove it. If we type in what e to the 5 power minus, no, plus rather, e to the negative 5th, and we divide that by 2, we get is 74.21. But if we also just do e to the 5th divided by 2, we get 74.21 still. So it's more or less the same thing because e to the negative 5 is so small it barely contributes much of anything. We get about 74 point, if you keep the original, I'll say 2009 or 2099. Okay. So that would be how to use the actual formulas to find numerical values. Now what we're also going to use those formulas for is to calculate specific proofs. One of the first proof we're going to keep in mind is something similar to the Euler's function, which is what happens if we just put cosh and sinh together. If we add cosh plus sinh together, know that they're both over 2, so they're very easy to combine. And what you notice is that the plus e to the negative x and the minus e to the negative x will cancel each other out, leaving just 2e to the x over 2, or just e to the x. So we get something that looks a lot like Euler's function. Just cosh plus sinh equals e to the x. Now, these are mostly the basic identities, the ones for how what cosh and sinh look like in terms of exponential functions. But we have a lot of the other ones that are going to look a lot like the ones from 1060, from trigonometry. First being the concept of odd versus even. In trigonometry, we have that sine is an odd function, and likewise sinh is also going to be an odd function, which means that if you plug in negative x, you can pull the negative outside the function. It is symmetric with respect to the origin, so you can spin it around. Whereas cosh, as we even showed before in the graph, is symmetric with respect to the y-axis, so it is considered an even function. It means if you plug in negative x into cosh, you get the same thing as just what cosh of x is, so the negative can be eliminated if you so please. Now, the same is true for the other 4 functions. Secant is considered even, and likewise here, sec is also considered an even function. The other hyperbolic trig functions are all considered odd. Now, what we also have are some identities that are in the same form as the Pythagorean identities. So the Pythagorean identities I have identified over here, the ones from trigonometry, so these are ones you should be familiar with. Or at least the first one, because all you need is really the first one to identify the other ones. You can divide each side by sine squared or cosine squared in order to solve for these other two. But we have sine squared plus cosine squared equals 1 and the other two functions. Now, the hyperbolic Pythagorean identities, which isn't really its particular name. They don't really have a group name themselves, so I'll just put in quotes hyperbolic Pythagorean because they act the same way. In this case, the first one is cosh squared minus sinh squared equals 1. And the second one is 1 minus tan squared equals sec squared. And then cosh squared minus 1 equals kish squared. Now, if you have trouble with these, what I want to point out as a way of trying to remember them, particularly if you know the Pythagorean identities, take the Pythagorean identities, switch the places of the terms. So for example, sine and cosine, switch their places, because this is how we would typically list it, and then put a minus in the middle instead of a plus. So we switch places of sine and cosine, put a minus in the middle, and then there you go. You got your hyperbolic Pythagorean identity. Same is true for tangent. Switch tangent and 1, and you get 1 plus tangent squared. Make it a minus, and you get tangent squared. And then lastly, 1 and cosh. So if you switch 1 and cotangent, you'll get cotangent minus 1, and if you make that hyperbolic, you make the middle a minus, and you're done. So that's a nice pattern way of identifying the difference between the two. Now, I don't want to just leave them there and say, hey, these are true, trust me. We're going to have to be able to identify and determine both of these and solve for them. So we're going to prove some of these. First, cosh minus sinh. The first one's going to take some time. The second one's not going to take much time at all. So cosh minus sinh equals 1. And I'll move it in the other way. I'll say, we can keep it this way. We can say cosh squared x minus sinh squared x equals 1. And what we're going to do to prove these is replace with what we know. In this case, I don't want to mess with the other side of equals 1, so I am going to keep that the same as I go through this. But I am going to mess with cosh and sinh because I know how to simplify with each of those. Cosh we know is e to the x plus e to the negative x all over 2. And this is a quantity squared. Minus sinh, which is e to the x minus e to the negative x all over 2. And because it's sinh squared, this quantity is squared. We want to show that this is equal to 1. The reason we don't want to mess with the other side is because if I'm trying to prove this, I don't know if this is true yet. So my goal is to show that this equation is valid, not to assume that it is and simply add or subtract to both sides, which I can only do if I have an equation. Okay, so if I square these, what I get e to the 2x. Basically, I'm going to be foiling these. And then I would get e to the x times e to the negative x, and I would get 2 of those. E to the x times e to the negative x is 1, times 2 is just 2. And then when I do e to the negative x squared, I get e to the negative 2x. And then the 2 on the bottom is going to get squared as well to 4, but so will the other side. So I'm just going to keep this all over 4. For sinh, I get minus e to the 2x again. When I do e to the x times negative e to the negative x, I get negative 1. Times 2, I get negative 2. And then times that other negative out front, the distributed negative, would make it a plus 2. And then lastly, negative e to the negative x times itself would be positive e to the negative 2x, and then the minus out front will make it another negative. So minus e to the negative 2x. Now here, it expanded a lot, but it's about to contract very quickly. E to the 2x cancels with minus e to the 2x. E to the negative 2x cancels with minus e to the negative 2x. And then I just get 2 plus 2, otherwise known as 4, over 4, and 4 over 4 equals 1. So I have confirmed that this proof is valid, that one side equals the other. Now, since I've done that, since I've proved this, that means that I now know that this proof is valid, that this equation is valid. Therefore, I should be able to use it. So, in order to prove this one, what I'm actually going to do is start with what I just had, cosh squared minus sinh squared equals 1. And what I'm going to do is try to determine what cosh squared is. Cosh is, or which treats just like cotangent, is the same thing as cosh over sinh, or cosine over sine. So what I'm going to do is divide everything here by sinh squared. Now you may be asking, wait, you just said that you can't mess with both sides because you don't know that it's valid. However, again, I do know that this one is valid. I know that this equation is valid because I just proved it. If there's anything that I've proved in the past, then I should be able to use it to help solve anything in the future. Now, cosh over sinh, that is coch squared. Sinh over sinh is 1, and 1 over sinh is kish. And there we go. Easy peasy. So just like with the normal Pythagorean, if you know the one, you can establish all the rest. Now, a couple other identities we can make. Now, the rest of these two examples that I have here are other identities that you can have, and a lot of the examples on your homework will act like this, where it asks you to prove identities, and you can use anything that you've solved up to that point in order to prove it. So I have cosh of x plus y. Move this up a bit. Cosh of x plus y equals cosh of x, cosh of y, plus sinh of x, sinh of y. And I'm going to try to prove this. This should look very familiar as an addition and subtraction identity from trigonometry. However, like back in those identities, I cannot start assuming that is true. I need to show that is true. So what I'm going to have to do for each of these is substitute, and it's going to take quite a bit of substitution. So cosh x is going to be e to the x plus e to the negative x over 2. Cosh y is e to the y plus e to the negative y all over 2. And then sinh of x and sinh of y are going to look very similar, just with the minuses in the middle. So minus e to the negative x over 2. And e to the y, e to the y minus e to the negative y all over 2. Okay. Now, what I need to do is I'm trying to establish cosh of x plus y. So what I'm going to have to do is start to multiply these together before I can add them all. So the first one is all going to be over 4, so that's easy. And the second one's also going to be all over 4, so that's easy. But when I try to FOIL these, I get e to the x times e to the y is e to the x plus y. And I'm going to get then e to the x times e to the negative y is going to be plus e to the x minus y. Then e to the negative x times e to the y gives me e to the negative x plus y. And then e to the negative x times e to the negative y would give me e to the negative x minus y, or e to the negative x plus y. Again, when I get e to the negative x minus y, I can take out that negative out of each of those to get e to the negative x plus y. That's why I did that last step. And I could do the same thing with the sinh formulas as well. I get e to the x plus y. Then I get minus e to the x minus y minus e to the y minus x, or negative x plus y. And then I get plus e to the negative x plus y. Alright, you'll notice a trend in terms of these tend to expand and then contract very quickly. I have e to the x minus y will cancel with this minus e to the x minus y. And then e to the negative x plus y will cancel out with the minus e to the negative x plus y. So all those will cancel out. And then each of these are doubled. So I have one of those there and one of those there. So I have two of them, 2 e to the x plus y. And I also have 1 and 2. So I have 2 e to the negative x plus y all over 4. I can simplify there with the coefficients to just get e to the x plus y plus e to the negative x plus y all over 2. And hopefully now you see why I made this minus quantity x plus y, because now this looks exactly like the form of cosh. If you even want to say, all right, make u equal to x plus y, then you can make this e to the u plus e to the negative u over 2, and that is definitely the form of cosh u, or cosh of x plus y. However, really at this point you should be able to state that this is cosh of quantity x plus y. The math here proves it, so we should be able to stop here. But you can continue this way if you want to use a substitution method. Alright, so that's how we will generally prove these formulas. Now these can be a little difficult at first, so I want to do another one at least. Now this is going to be something similar to the double angle identity. We have cosh of 2x equal to cosh squared of x plus sinh squared of x. Remember that before, cosh squared minus sinh squared equals 1, but if we add them, that supposedly equals cosh of 2x. Now, in this one, just like the last one, what I'm going to work with is the complicated side, the one that has more stuff going on, because typically that has more options for manipulation. You always want to work with the most complicated side first. So cosh squared x is e to the x plus e to the negative x, quantity squared. And then sinh squared is e to the x minus e to the negative x, all over 2, quantity squared. Now you can also substitute cosh of 2x and make that e to the 2x plus e to the negative 2x over 2. However, I will refrain from doing so. I think it's best, it's cleanest to do a proof by just messing with one side and get it equal to the other. Tends to be the best way to do it. So this one expands to give e to the x plus, or e to the 2x rather, plus 2 plus e to the negative 2x all over 2. And we did something like this before. And then up over 4 rather, not 2. And then for the second one, we get e to the 2x minus 2 plus e to the negative 2x all over 4. So this should look kind of familiar with what we did with the quote-unquote hyperbolic trig functions, or hyperbolic Pythagorean trig functions. When we established that, though, we had that all the exponential functions eliminate each other, but in this case, the only functions that will eliminate is this minus 2 and plus 2. Those are the only two pieces that will cancel out. Everything else will combine. So we get 2 e to the 2x, just like with the previous proof, plus 2e to the negative 2x all over 4, which is e to the 2x plus e to the negative 2x all over 2, which is the same as cosh of that exponent there, of 2x. So we proved it, and that's all we need. Again, if you want to go further and say u equals 2x, and then say that this is e to the u plus e to the negative u over 2, which is of the form of cosh of u, or cosh of 2x, that's also fine. Depends on how you would like to approach the proof. Okay. Now we have a little bit more. We have a couple more pages. So this has a lot of stuff to do, and I wanted to show a lot of examples. We can also define definitions for the derivatives of each of the hyperbolic trig functions. First, what we're going to do is show how one of these derivatives would be derived by finding the derivative of cosh x. So, like with the previous functions, the way that we are going to derive this thing is by using the definition of cosh in terms of the exponential functions. So if I'm trying to find the derivative of cosh x, what I need to do is think about cosh in terms of e to the x plus e to the negative x over 2. Hopefully I'm saying these enough and you're writing them down enough that you'll start to memorize these ones for cosh and sinh. Well, if I take the derivative of each of these, that over 2 doesn't really matter. You could treat that as a coefficient on each of them. You could treat this as the derivative of 1/2 e to the x plus 1/2 e to the negative x. So the coefficients don't really matter too much. And what you get is a derivative of each. The derivative of e to the x is e to the x, so you get 1/2 e to the x. But the derivative of e to the negative x is going to be negative e to the negative x. That exponent, the derivative of the exponent, is going to come down via the chain rule. So we'll get minus 1/2 e to the negative x. Or, if this looks familiar, this is e to the x minus e to the negative x over 2, which means that this is sinh of x. So we have that the derivative of cosh is sinh. Now that may strike you a little bit weird because the derivative of cosine is negative sine. They actually change signs. That is going to be one of the small differences with the derivatives of the hyperbolic trig functions. And we have all of them listed down here. We have derivative of sinh is cosh, which sounds familiar to the normal derivatives of trig functions. Derivative of cosh is sinh, we just did that. And derivative of tanh is sich, also should be very familiar. Then derivative of kish is negative kish times coch. Derivative of sich is negative sich times tanh, and derivative of coch is negative kish squared. The only two differences here, really, are this one, the derivative of cosh equaling to sinh. In that case, the signs are a little bit different. And the other one is the derivative of sich. The derivative of sich, or secant in trigonometric form, the derivative of secant is positive secant times tangent. But in terms of derivatives of hyperbolic trig functions, it's negative instead. So it gets flipped. So these are the only two that really differ from the standard derivatives of trig functions. You can also notice as a pattern, all the standard trig functions, so sine, cosine, tangent, the ones that are not the reciprocals, all lead to positive derivatives, whereas the reciprocal hyperbolic trig functions all lead to negative derivatives. Now, since we know these, what we can also do is solve for some more complicated derivatives that involve both of them. So if I'm doing the derivative of y equal to natural log of sinh x, I'm trying to find what y prime is. So I'm trying to find the derivative of natural log of sinh x. So in order to do that, what you can do is consider this as u. If you're unfamiliar with it, you can say, all right, well, derivative of natural log of u. And the derivative of natural log of u is du over u. So that means that this is going to be the derivative of d dx, the derivative of sinh x all over sinh. Well, the derivative of sinh x we've shown earlier is cosh over sinh. So the derivative of sinh is cosh, and then we have that divided by sinh. And cosh over sinh is coch of x, dx technically. So that's what we're looking for. So the derivative of natural log of sinh x would be coch x. Nice and easy. Same for the derivative of e to the cosh of 3x. So y prime, so we're looking for the derivative of e to the cosh 3x. You can do the u substitution if you want to. The derivative of e to the anything is that same function times the derivative of the inside. So we're going to get e to the cosh 3x, and then we have the derivative of cosh of 3x. Well, the derivative of cosh is sinh, and then that 3 would then also come out if you do the chain rule there. So what we would overall get as an end value of this is 3 times sinh of 3x times e to the cosh of 3x dx technically. That's what we would be looking for the derivative of this function. Alright, so once you're solving for those and you know the derivatives of the standard functions, you could treat them just as if you were dealing with anything with the other trig functions. Now, since we also know the derivatives, that should also lead to the integrals for the hyperbolic trig functions. These are also available in the back of your book, if you so please. And a lot of these should make a lot of sense. And they should be kind of familiar to the normal trig functions. For example, the integral of sinh is cosh, the integral of cosh is sinh, so a lot easier, and then we have the plus c's unless we have the integration bounds. Integral of tanh is natural log of cosh. Integral of kish squared is negative coch. Integral of sich squared is tanh, and integral of coch squared is natural log of sinh. Now notice that there are two functions that have natural log, and the reason that only one of these has an absolute value is because if you remember the graph of cosh looks like this. It's always positive anyway, so it doesn't really need to have the absolute value. Whereas the graph of sinh look like that. So it is sometimes negative, so it does need the absolute value because natural log, the inside of a natural log cannot be negative. Okay. Now, we also, to end with, have what are the inverse hyperbolic trig functions. Remember, these are what allow you to, like what we had for the inverse trig functions, where you start with a ratio of sides, and then you can find the angle that corresponds to that. Whereas typically, when you're just dealing with trig functions directly, what we're doing is plugging in an angle and getting a ratio of sides that corresponds to the circle. So we have here what the inverse functions do, and they do the exact thing that you'd probably expect. The inverse of sinh x is the same thing as doing sinh of y equals x, so they're just kind of switching the places. Because what you would do to get y by itself here is apply sinh of -1 to both sides, since they're inverse functions. Now, the one thing that we do need to restrict is for cosh, however, because unfortunately cosh is not one-to-one as we established earlier on the first page at the end. It is not one-to-one because not every x leads to a unique y. So therefore we need to restrict the bounds for y to be from 0 to infinity so that it is only using the positive or one version of it that is the one-to-one functions. So we do typically need to restrict that, but that's not going to matter too much. We can define the inverse hyperbolic trig functions in another way, and we can consider that since we can define the hyperbolic trig functions using exponential, it's standard to reason that the inverse hyperbolic trig functions would also be defined using inverse operation of exponential functions, so natural logarithms. So since the original sinh, cosh all used e to the x or e to the negative x in various places, and we're finding the inverse of sinh and cosh, it stands to reason that we'd be using a lot of natural logs. So what we're going to do is show how we would define sinh inverse using a natural logarithm. Okay, so the way that we're going to start with this is that we have y equals sinh inverse of x, and we know that this is defined as x equaling to sinh of y. And we can take this sinh of y and expand it out using the fact that we know that sinh of y is e to the y minus e to the negative y all over 2. Then what we can do is multiply that 2 to the other side to get 2x equal to e to the y minus e to the negative y, and then move everything to the one side. So we get 0 equal to e to the y minus 2x minus e to the negative y. Our overall goal here is to try to get y by itself again, without having to use the sinh function itself. Now, that's a little bit complicated, but what we can try to do is try to make this to look like a quadratic. And to do so, we notice that this is this is similar to a quadratic because we have degree 1, degree 0, degree -1 for those exponential functions. So what we can do is take both sides and multiply by e to the y. That gives us 0 times e to the y is still 0. E to the y times e to the y is e to the 2y. Minus 2x times e to the y is minus 2x e to the y. And e to the -y times e to the y is minus 1. So now this looks like this looks like a quadratic. Power of 2, power of 1, power of 0. So what we can do is say, all right, well, if this is our variable, if our variable is e to the y squared, or e to the y to the 1 power, what we can do is try to say, all right, let's do a quadratic with e to the y equaling to negative b plus or minus, etc. So negative b, where b is minus 2x, would be 2x plus or minus the square root of b, which is, again, 2x squared, minus 4ac. So we have 4 times a, which is, in this case, 1, times c, which is -1, all over 2a, which again is 1. Well, this works out pretty nicely for the most part. We see 2x plus or minus. We can start to simplify the inside. I have 4x squared plus 4 all over 2. And what I can do is I can actually see this 4 inside of this quadratic, or this square root, and what I can do is factor that out, make this x squared plus 1. And if I pull that 4 outside of the square root, I get a 2, which cancels out with this 2. So this 2, that 4, and that 2 will cancel out to get x plus or minus the square root of x squared plus 1. The only other thing that we need to know is that since this is equal to e to the y, the graph of e to the y is always positive. It's always above the axis. Therefore, we don't even need to consider the minus here. We can completely eliminate that. You know that's only going to be a plus. It's the only one that makes sense. And to get y by itself now, all we need to do is apply a natural log to both sides. So natural log to both sides, and we get y equal to natural log of x plus the square root of x squared plus 1. So that would be our solution, because we know we have y, which we defined as sinh of x before, so we have our solution for what sinh of x is equal to. So it's another way of defining sinh of x as the natural log of x plus the square root of x squared plus 1, all under the natural log. So that'd be a proof of how we would do that. And I have the other functions listed here for that. So cosh is going to look pretty similar. The only difference is that there's a -1 here and is restricted for x is greater than or equal to 1. And you have tanh is equal to this function here with these bounds. And you can solve for the rest of these. I think you may have a homework or two problem that asks you to do so. So you're going to work through a similar process as before to solve for those. Lastly, the derivatives for all those functions. The derivatives for the inverse functions are listed here. Again, that'd be basically just doing a derivative of one of these and then solving. And since the derivative overall is a natural log, it makes sense that most of this gets pushed to the bottom side. So you can solve for all of those if you so please. Overall, that about covers it. There's a lot of derivatives there. Some of them you need to know and memorize. I usually recommend knowing at least the basic hyperbolic trig functions and be familiar with some of the other typical ones. So usually like the inverse sinh, inverse cosh, because you should be able to transverse other trig or inverse trig or your hyperbolic trig into sinh and cosh and work with it appropriately from there. So that's typically the easier way of going about it. Yeah, just keep in mind as well as you go through the homework and as you think about what we've done here, if something has already been proven, then you should be able to use that in other proofs. And what you're going to do in a lot of the homework problems is consecutively make a lot of proofs. So particularly for, I think it's 5 through 10 or so. So if you've proved anything in those, you should be able to use those in later problems if they apply. That can help save a lot of time. So I recommend keep everything that you've made in mind. But with that said, that's everything that I wanted to show. If you have any questions, feel free to put them into the comments below or ask your instructor directly. With that said, I hope you have a nice day.